So it's my great pleasure to introduce Tao Du, who's visiting us from MIT CSAIL. Tao is a postdoc with Wojtek Matusik and Daniela Russ, and is doing really exciting work bridging together physical simulation, machine learning, and numerical methods to solve inverse dynamic problems that have wide applications in both computer graphics and robotics. And his work has been featured in the top robotics and graphics journals, and we're super excited to hear him tell us more about it. So thank you, Tao, for joining us.
Thank you very much, Adriana, for the introduction, and thank you everyone for joining us in person and online. So I'm going to do the talk first, and let's save the questions at the end of the talk, and I will leave enough time for that, hopefully. So it's my great pleasure to be here, and today I'm excited to share with you guys a story of a series of methods that we developed in the past few years for solving inverse dynamic systems and problems. So what is a dynamic system? So this is a very common concept in scientific and engineering research. For example, in robotics, engineers and scientists study dynamic systems and use them to model complex, fairly complicated robots like this very famous animal quadruped from ETH Zurich. And in biology, molecular biologists also study dynamic systems and use them to understand the behavior and chemical reactions of molecules. And similarly, in meteorology, scientists study the dynamic systems of atmosphere to understand the pressure, temperature, and precipitation. So in this talk, I'm going to steal the definition of a dynamic system from Nature Portfolio, which states that a dynamic system is a particle or ensemble of particles whose state varies over time and thus obeys differential equations involving time derivatives. So there are two key points here. So a dynamic system is characterized by states, and the states are time dependent, and it is confined by some rules, which is typically described using differential equations. So let's write it down in a more formal way. So here I'm using S to indicate the state of the dynamic system, which is actually time varying, and we also have the time derivatives to a certain amount of orders. And they are confined by a f function which defines the dynamic system itself, and f is typically a partial differential equation or an ordinary differential equations. And there are lots of examples of how f can be defined, and this has been very well developed and well understood for decades or even centuries. For example, for robotics, you might be very familiar with articulated body systems, whose dynamic is characterized by the famous Euler-Lagrange equation. And graphics people are also familiar with deformable object simulation and fluid system simulations. And these both have their own corresponding dynamic systems and the governing equations behind that. And of course, a dynamic system or a model itself is incomplete without specifying the parameters. So here I am clarifying the inputs and outputs that we typically consider for a dynamic model. And specifically, I am calling parameters as an input to the dynamic system because you need to specify them and initiate them before you can run the dynamic systems. And I'm going to classify the parameters into two categories. Some of the parameters are intrinsic parameters, meaning they are inherent to the dynamic model itself. Examples can include, like you are using a CAD software to design the geometry of your robot, and then the width, length, inertial tensor, mass properties. This becomes the intrinsic parameters of your dynamic model. And they will be embedded into somewhere hidden inside the governing equations. And there are also a set of parameters that I call extrinsic parameters here. So these are something that you need to specify as an external parameter to the dynamic systems. Examples include, like you have an open loop control sequence you want to send to your dynamic system, or for example, for fluid systems, you want to specify the initial boundary values. So these are something that is not bounded to a particular governing equation, and you have the flexibility to tune them or modify them from time to time. And with the model and the parameter being specified, you have full description of a dynamic system, and then you can use that. So by using that, I mean I can try to solve the governing equations, solve the partial differential equations using numerical integration or other numerical tools that will reveal how the states evolve over time. And this gives us a sequence of states after proper time and spatial discretization. And as you can probably imagine, this is closely tied to physics simulation, which generates states from solving and writing the governing equations. And alternatively, you can also gather this state information from real-world experiment, which also follows the underlying dynamics rules. So there are two types of questions that people are interested in when studying dynamic systems. And they are called the forward problem and the inverse problem. So the forward problem is straightforward to understand. This is basically what I just described. Given the model and the parameter of a dynamic system, you want to compute the states and the sequence of the state, and you want to understand how this evolves and use that to compute some performance metrics that you care about. So using this diagram to explain this idea a little bit more, it's like a linear flow of information where you have the specification of your parameters, you have the rules that characterize your model itself, and then you basically run physics simulation or other types of numerical tools to evaluate the performance based on the output action, the state sequence. And of course, forward dynamics problems has been widely used in many fields, scientific and engineering fields, in particular in robotics study. So the two papers I'm showing here both presented, let me see if I can play the video. Oops. So this uses the Navier-Stokes simulator in COMSOL, which is a widely used commercial software for solving fluid simulations to predict the performance of an airfoil design. And this is one example using forward dynamics tools to help you understand the dynamic problem. And similarly, on the right, there's a Dexteros hand, which is implemented using Isaac Gym, a simulator developed by NVIDIA. And this also is a standard example of running forward simulation or forward dynamic problems, where you specify the input hand parameters and the actions, and then you try to simulate the motion of the action of the hand playing with a cuboid. And with the forward problem defined, we can now talk about the inverse dynamic problems, which is what this talk cares about. So inverse dynamics problem basically flips the input and output of the dynamic systems. And in one short sentence, this is trying to solve the following problem. So given the state sequence of a dynamic system, try to find the proper parameterization and model that can realize the state sequence. So that's why I'm calling this inverse model and parameters. So using the same diagram here, I'm basically flipping the direction of the arrows. So now from the rightmost evaluation, you kind of have some information in mind that you want the system to behave like. And then you try to go trace back to see how you can basically demystify the proper model and the parameters that can realize what you really care about when you are calculating the performance metrics. And to give you two concrete examples how inverse dynamic systems can be helpful in scientific study. So these are two very recent papers relatively recent papers from the graphics community. And on the on the left, there's this is the real-to-sim paper where you have the real-world dynamic system, which is the elastic rod, and you kind of gather the local the motion sequence from running motion capture systems, and your goal is to reconstruct a digital twin in your simulator so that you can reliably replicate the real-life motion of this elastic rod. And as you can probably see, they did a reasonably good job in reconstructing the parameters and underlying models for this. And another example is for inferring the what I call the extrinsic parameters in the dynamic model, and this is called the deep mimic, which is also a famous paper from the graphics community. And in this work, they gathered again also the motion capture data of a human being doing this very complicated head spin. And the goal is to basically reconstruct the same motion sequence in a virtual environment. And as you can probably see, this requires you to infer the action sequence, and they did a very good job matching the simulation and the reference data. So, of course, hopefully you are now agreeing with me that inverse dynamics problems is seemingly much more difficult to solve than the forward version of the problem. This is because for the forward problem, you kind of know the full description of your model, and you just do forward thinking and evaluate the model, and you get the data. But the inverse problem is like you have a black box, and you need to look inside and try to decipher the black box and find a proper realization or implementation. And the talk today is going to introduce a family of methods, what we call the gradient-based approaches that we developed in the past few years that try to give you guys a systematic methodology for solving the inverse dynamics problems. And as a disclaimer, I have to say this is not the only way, of course, to solve the inverse dynamics problems, but we have some very interesting attempts and some interesting lessons that we would like to share with others during this endeavor. So the first category of the approaches we developed is for deriving gradients and using the gradients with respect to parameters in the dynamic model. And this leads to some interesting works about optimizing the shape and control parameters for a soft fish, which I'll talk about later, and also for a rigid body system. And a second category of leveraging gradients is to figure out how to basically calculate the gradients with respect to the model itself. And this is echoed as the differentiable physics or differentiable simulation problem, which becomes an active area in the past few years. And we also have some interesting explorations in this direction, where we will present 2 differentiable simulation papers we built at the SIGGRAPH this year. And finally, there's also some interesting discovery that by using the gradient information in the evaluation step, you can also find some benefits and try to use that to guide your search or exploration. And this leads to the iClear paper, which will be presented shortly in a few weeks. And in this talk, I'm going to pick one out of each category and focus on introducing 3 representative papers in this whole family of gradient methodology. Okay, so let's first start with the DiffAqua paper. This is going to be about how we can use gradients to do some very interesting and meaningful parameterization of the problem. Okay, so the problem statement is as follows. I think once, I think this was like 5 or 6 years ago when we were chatting with other lab mates at MIT CSAIL, and people came up with this idea that we would like to build the soft robotic fish, and we would like to build the best soft robotic fish in the world. And how do I define best? Basically, I'm trying to find the optimal shape and optimal control of a robotic fish. And I have some certain tasks that I want my robots to finish. Like I want it to be flow resistant, or I want it to be extremely like a faster runner or swimmer. And the statement, roughly speaking, is that you have a set of the tasks, and you have some performance metrics, and you want to find the optimal shape and controller of your fish, so that you can score very well in these tasks. And why do we care about this? Because there are many exciting scientific applications of soft robotic fish. And I'm showing 2 very representative works that I'm aware of. So the left one is Sophie. This is a soft robotic fish built at MIT CSAIL a few years ago. And this is a prototype that is a handcrafted, manually designed prototype. But it did very well in an underwater environment, and it helped the scientists to understand the ocean dynamics and the marine creatures. And there's also, I believe, an ongoing project, SETI, which is a collaboration between MIT, Harvard, and National Geographic, and a few other universities where people try to understand the language that sperm whales speak. So this also requires you to have something that is close enough to observe and interact with sperm whales and record their behavior, demystify their language. So this also requires you to have some underwater robots. And why do I say this is an inverse dynamics problem? If you look back at the diagram that we talked about before, so we kind of know the evaluation or the desired performance that we want to achieve. For example, if I want to design the fastest possible swimmer, my performance metric would be just to measure the horizontal speed or horizontal offset over a certain amount of time interval. So you kind of have a good idea of what kind of expected behaviors you want to see from your design. And you also kind of know, you have a roughly good understanding of the modeling here. So this is a softer fish, we understand that. So it's going to be modeled as, what we choose here is a continuum mechanics and plus some finite element methods. So very well developed mathematical and theory behind that. And we kind of know how to write the simulator for this. And what we are not knowing right now is what would be the proper shape design and the controllers that can realize such a good fish so that it can swim, let's say, as fast as possible. That's why we say this is an inverse dynamics problem. And if you think more carefully about the challenges here, there's something very unique about designing soft robotic fish. And there are at least two challenges that we encountered when we were working on this paper. So the first one is, if you think about the softer fish, they are soft by definition. So that means they have tons of degrees of freedom if you want to simulate them. And characterize their full motion. And the second, maybe less obvious challenge is that fishes are actually very diverse. They have a various different morphologies with different numbers of fins and limbs. And it's very difficult to find one compact representation that can uniformly parameterize all of them. So to give you a more concrete idea about the problem we are faced with, consider here are three different prototypes of softer robotic fishes. And they are realized using finite elements method on a regular grid. And each of them requires roughly 40K degrees of freedom to define their shape. And so this basically highlights the first challenge, that they have lots of degrees of freedom to deal with. And if you count the number of the fins, you can also notice there are various morphologies differences here. So this is a second challenge, that how you are going to uniformly represent a design using a mathematically rigorous way and explore in this design space. Or maybe take a step back, how are you going to define the design space here? And the key observation we're making here is that we claim that a good parameterization is the key to this problem. And here's the one that we propose in this paper, which is called the Wasserstein gradients. This is obviously derived from the Wasserstein distance. And it is a very unique way of interpolating between different bases while maintaining some smoothness and topological changes. And here, if you look at the video in the middle of the three circles, this is showing the smooth interpolation between the three base fishes. And as you can see, it morphs very slowly but smoothly between different shapes. One of the most exciting things that when I was looking at watching this video is that you can notice that the number of the fins also changes in a reasonable way when you are navigating between the different designs, or more concretely, the different ways you assign to each of the designs. So what is the benefit of this parameterization? The benefit is that now you drastically reduce the degrees of freedom in the design space to only 3, or actually, to be more exact, only 2, because you have the constraint that the weights have to sum up to 1. And on the other hand, you also have a reasonably defined parameterization that can morph between different designs while still have the reasonable number of the fins and the fish shapes. Imagine if you are doing that instead using, for example, linear interpolation. then what you would expect is that you will see like overlapped shapes from two of the bodies, and you will have smaller and more tinier things around the shape, which is not ideal for the purpose of designing an efficient swimmer. And once you have this kind of the parameterization, and let's say if I instantiate the design with one set of parameters, I can run forward simulation, and I can calculate the score that I care about. And in this particular case, I care about the horizontal speed it travels. And then I can compute the score based on the simulation output. And then basically I flip the arrows back towards the very beginning of the design parameters. And along each arrow of this diagram, we develop the gradients. And we derive gradients using some mathematical tools. And this allows us to basically backpropagate the influence of each of the score function to every single design parameters. And the gradient descent algorithms can follow up afterwards. So let's see some results here. So the first results that we're presenting here is exactly from the previous slides, where we try to design a speedy fish. And the top three arrows that you saw is from exactly the three base shapes at the three corners of the triangle. And for each of them, we optimized the controller and kept the shape fixed. And then we simulated them for 4 seconds. And here they stopped at the location basically where they are after 4 seconds. And below, at the very bottom, you see that if we are allowed to jointly explore both the shape and the controllers, we're able to actually reveal something different and something new, something that cannot be realized by just optimizing the controller only. And this turns out to be actually a better design in terms of the traveling speed. So this shows the value of navigating into the interpolated space of the three base fishes, and it will give you something unexpected, but in a good way. And the second example that we showed in the paper is to design this so-called flow-resistant fish. And for this one, we are scaling up the base libraries from 3 to 12 designs. And the radar map on the right shows the average the weight we assigned to each of the design, both before optimization and after optimization. And on the left, you see two videos where we use the red and the blue circles to indicate the center of mass of the fish and the target location where we want the fish to stay, respectively. And as you can see, before we optimize the fish will basically, I should have mentioned that there's a flow, constant flow, pouring into the scene from right to the left. So before optimization, you see the fish is difficult to counteract the flow and is basically retreating. And after we optimize the shape and the controller, the fish can actually stay roughly where it is and realizing the goal of becoming a flow-resistant fish. And there are a few other examples shown in that paper, and also a follow-up and related work that we did later that year is to try to see if we can actually use the same gradient idea and realize them on real hardware. So this is the RAL paper we had last year, where we basically try to design what we call the soft starfish robot, and parameterize this controller and optimize the controller and system parameters based on gradient descent algorithms. And but I'm going to skip this paper and move on to the next one. But you're welcome to check it out on my homepage. Okay, so just to do a quick summary. So what we have known so far is that we have presented a way of running gradient descent and with respect to parameters in a dynamic model. And we showed that by carefully deciding where you want to parameterize and how you want to parameterize the design space, gradients can come into play and try to do something useful and good for you. So now we're going to move on to the second phase in this inverse dynamics problems, which is about the deriving gradients and using gradients in the modeling process. This is essentially what people are nowadays called the differentiable simulation or differentiable physics field. And this is also essentially the differentiable simulator behind the diffaqua paper that I mentioned earlier. So this paper, diffPD, is going to be presented at SIGGRAPH this year. And I'm just going to skip the technical details behind the development and highlight some features of this differentiable deformable body simulator. So basically, we're thinking about 3 competing goals that we want to make when we're trying to develop this differentiable soft body simulator. The first goal is that you want to have gradients. You want it to be a differentiable simulation. And the second goal is that you want to have a faster simulator, and you don't want to wait for too long, because it can be it's typical that if you run deformable body simulation, use finite element methods, you can wait for hours to see the results. And the third goal we had in mind is to have implicit Euler time integration to ensure numerical robustness. And I have to mention and give enough credits to all of these previous papers, which are actually laying a very strong foundation for us to develop the diffPD paper that we hopefully can claim lies at the intersection of the 3. So there are actually very, very useful differentiable simulators in the previous years that attempted to realize as many goals as possible in the figure. And what we are doing is that we're basically standing on the shoulders of these giants and combine some very interesting mathematical insights into the problem and got something that can strike a good balance between the 3. So let me just show a few examples to sketch out what this differentiable simulator can do. The first example is what we call the system identification task, which is typical in inverse dynamics problems. So the goal here is that imagine you have a motion sequence of your dynamic system. And in particular, in this case, we're interested in understanding the motion behavior of this rubber duck, which is very, very soft. And the goal here is to try to infer some of the system parameters. And in particular, in this case, we're inferring the frictional coefficient and the frictional models between the curved surface and the duck. And by running this differentiable simulator, you can calculate the gradients with respect to the friction. And you can try to minimize that using gradient descent algorithms. And then what you can get is that you can realize the motion that hits the target goal, which is actually something that we intended to see from the output video. And another very typical and common application is trajectory optimization, which is I would say which is actually solved using gradients in a classical way, but mostly in rigid body and articulated body systems. There are not so many attempts that try to solve trajectory optimization for pure soft body systems. And hopefully we can say this example gives you some good demonstration here. So what we are trying to solve here is that we have this very cute what we call the torus or the donut robot, which is a software robot with 8 sectors of muscle fibers along the tangent directions. And the muscle fibers can extract, can basically elongate itself along the tangent direction or contract itself. And we also have some contact and frictions between the torus and the ground, so that by leveraging these frictional coefficients, you can roll yourself forward. And the goal here is that you want to come up with a sequence of the actions you apply to each of the muscle fibers, so that you can roll the torus as quickly as possible along the horizontal directions towards the right end. And as you can see, there's also we also compare the results before and after we optimized the control parameters. And with the help of the gradients from the differentiable simulator, we were able to push the performance a little bit more. And I'm going to end this paper with a real-to-sim transfer example, which is, in my understanding, also a typical setup for inverse dynamics problems. So what we are looking at is that on the left, we have a video clip of 2 colliding tennis balls. And the goal is to try to reconstruct the same thing, but in a virtual environment. And and in particular, what we're trying to infer is it's a frictional coefficient between the ball and the ground, and also the stiffness of the softer the tennis ball. And again, with the help of the gradient with respect to all of these parameters, we were able to run gradient descent optimization algorithms. And before and after optimization, we were able to match the trajectory from the video clip more closely. So hopefully this gave you a good idea of, or a good sense of what nowadays a differentiable simulator can do or can help in terms of solving inverse dynamics problems. And in the final phase of this diagram, we're going to move on to talk about the gradients with respect to evaluation, or the gradients you calculated during the evaluation process, and we'll show that this can actually have some very interesting and positive side effects to your problem. And to demonstrate this point, I'm going to present this RISP paper, which was recently accepted to ICLR 2021, and this will also be presented at ICLR in 2 or 3 weeks. So you're more than welcome to check out our talk and to chat with us during ICLR. So the goal here is to consider the following inverse dynamics problems. So what we are looking at is a real-world video clip we took at MIT, where we're controlling a drone, a quadrotor, and there's a pilot outside the video that constantly send manual control signals to the drone, and the drone is drawing some trajectory. And the goal of us is to build a digital twin of this video in a virtual environment. And this requires us to mostly reconstruct the dynamic information about this drone, including the states and the actions, and also some system parameters. And why do I say this is an inverse dynamics problem? Because we have some good understanding of the evaluation or the performance metric that we have in mind. And this is a particularly very specific. We have the motion sequence from the video, and we want to match them. We want to basically build a virtual quadrotor, and that can match the motion sequence. But we don't know the action states. And the dynamics is also straightforward and I would say very, very well understood for quadrotors. It's a standard Euler-Lagrange dynamics, and people have had some very good tools to analyze them and to realize them. So what is missing here is that we want to recover the control sequence that is to be decided. And it turns out to be a very, very interesting problem with some unexpected twists. So the first challenge that we identify is that if you are thinking about reconstructing a dynamic model from the video itself, there is some unknown visual appearance that actually shadows the dynamic information that you really care about. So what do I mean by this? To illustrate this point, I am showing you 2 pairs of the experiments that we did. Let's take a look at the top row first. So on the right, what you are looking at is the real-world video that we took. It's also the one that we want to match our virtual quadrotor with. And on the left, what you are seeing is a rendered quadrotor that we actually generated using some parameters and control sequences. So if you compare the left and the right one, you can actually see their trajectories are relatively similar. However, their visual appearance are quite different. I mean, obviously, one has a yellowish ground, and the other one has this silver-like ground. And on the other hand, if you compare the lower 2 images or videos, the right video is still the same real-world video we took, the video clip we took. But the left one is a rendered video. That one has a much more similar visual appearance to the input, but the dynamic information is very, very far off. And you cannot even see the quadrotor after the middle of the video, because the trajectory and the action sequence is basically too different from the input. So what we are really caring about here is to recover the dynamic information, but not the visual information. So this leads to the first idea that we think about in this paper, which is we're going to train a network. And we're going to teach the network to forget about or basically ignore the different visual appearance from the input video and try to output what it considers as the dynamic states. Let's imagine we have this network ready, and let's imagine we have trained this network very well so that it can do the job 100% correctly. So what does it mean? That means if I give you two different videos, the network should be able to basically ignore or filter out the visual discrepancies and focus more on giving me the dynamic trajectory that I care about. So on the right, what you are seeing is actually the underlying trajectory that we use to generate the top video and we collected from the bottom video. So this is what we want the network to behave. Basically, try to directly give me the dynamic information I try to match. And this is not a fundamentally new problem, and there are some established approaches to this. The most widely used approach is a domain randomization. And the idea behind this is relatively simple. Since you are not able to measure exactly what the visual components in your real-world video is, the idea is that I'm just going to randomize my renderer in the virtual environment. I'm going to generate different videos with different lighting conditions, different material properties, and different textures. And I'm going to feed all of them into my network and teach the network to basically try to ignore them and fit the underlying states. So did this idea work? We tried actually very, very hard to fine-tune the networks, but unfortunately, it did not work very well in this particular case. And this is actually the same video that I showed before, the bottom pair. And the left one, despite the force that we tried very, very hard to match the visual appearance we sent to the network still somehow forgets to recognize what is the true state information that we wanted to capture. So why did it fail? To understand this, which also led to the second idea we're going to talk about very shortly. So why did it fail? If we look more closely at the input to the video to the video clips, there are actually two things that matters if you think about how this video was captured. The first thing is, of course, the underlying dynamic model. So this is Newton's law, Euler-Lagrange equations that the nature runs to generate the states that leads to the motion of this robot. However, there's also another set of components, which is a visual appearance. This includes lighting conditions, material conditions, textures, and this is something that we don't have full control over, and we don't have ways to measure them. And it is actually the lower block, the visual appearance, that pollutes the neural network and makes it challenging for the network to basically inverse the top block. So if you think about the role of the neural network here, it has to somehow try to find a way to be agnostic to any variances in the visual appearance, the lower left block here. And we have tried that domain randomization is a way of tackling this problem, but it did not work very well. So the second idea we had is we will incorporate gradients. In some sense, domain randomization is like you are using zeroth order gradients, like you basically regenerate new data, but without considering its gradients. And then you try to let the network fit the data. And if I look closely at the argument that I want the network to be agnostic to visual appearance changes or variations, it is equivalent to state that the output of the network will have zero gradients with respect to the parameters in the visual appearance. So more concretely, if you have zero gradients with respect to, let's say, the lighting intensities in the scene, that basically means regardless of how you tune the lighting conditions, you should get the same output, which is what we actually want, which is the invariance that we want the network to have. So this is what we call the first order approaches comparing with the zeroth order domain randomization approaches. And there are some underlying mathematical intuition behind this, but the high level idea is that you incorporate this additional constraint in your training, and it actually, it magically makes the network behave much, much more robustly. And with a more robust network predictor, we will actually be able to reconstruct the dynamic motions, even if we are intentionally sending quite different visually looking videos to the network. So on the right, you see this is an input video that I kept talking about, and on the left is the one that we were able to reconstruct after we trained this network predictor. And another example we had is this has to be a video that I need to play. Is to do the similar thing with this dexterous hand. So on the leftmost video shows a target input, which is a articulated dexterous hand with some unknown control sequences that leads to the motion of all the fingers. And the goal here is to try to make an educated guess of the action sequences so that you will be able to imitate the motion of the hand from the input video. And in the middle, what you will be seeing is the reconstructed motion from running our approaches. It's not 100% ideal, but if you compare that with the reconstruction we got without using the gradient, you will see that there's actually a substantial improvement between the two. In particular, if you take a look at the motion of the fingers, you will see there's a difference and there's an improvement. And also note that we intentionally used different rendering and lighting conditions in the training domain and the target domain to basically stress test whether the network is robust enough to handle visual differences. Okay, so to summarize, in the last phase of this diagram, we're showing I would say, a very creative way of using gradients in the evaluation stage. And we're showing that by leveraging some kind of insights behind the gradients, you will be able to actually guide the training of a network model or of your dynamic models that can actually help you solve some interesting sim-real or sim-to-sim tasks. So hopefully this tells you some good lessons about why I believe gradients are or will be very useful in solving inverse dynamics problems. In the very last few minutes, I would like to wrap it up by sharing a story. And normally at the end of the talk, I will talk about the limitations of the gradients. But today, I decided to do something different. So let me share with you what I consider as one of the most inspiring inverse dynamics problems in human history. So it starts in the 16th centuries, where I believe the leftmost astronomer, I'll try to pronounce his name correctly. I believe it's Tycho Brahe, and so he was one of the leading astronomers in his time, and he collected lots of data and observed and collected lots of data for planetary motions in the solar system. And at that time, many brilliant minds in Europe were thinking about how do we understand the motion of planets. And it did not take very long for Kepler, the man in the middle, another very famous astronomer, to actually summarize a few today, which is known as Kepler's 3 laws, which actually summarized the motion from the data, tons of data that Tycho collected over years. And these are 3 elegant yet empirical rules that people learn from observing the data only. And it also did not take too much longer for Sir Isaac Newton, one of the most brilliant minds in human history, to show that actually the empirical rules that Kepler summarized could be a direct derivation from Newton's 3 laws of motion. So I'm thinking about this as the most inspiring inverse dynamics problems in history because, number one, it is, of course, the inverse dynamics problems. You try to understand the laws behind the planetary motions. And number two, if you look at how people study this problem, and if you think about what you are doing today, it actually shares a lot of similarities. So nowadays, we are also doing data collection, and we are running like machine learning models to do to do induction, which is like what Kepler is doing by summarizing the rules. And after that, we are still seeking a good way to basically laying the theory or find the good theoretical foundation after you summarize the few inductive rules. So what I'm thinking about as maybe one of the most important lessons I learned from this is that the most rewarding inverse problem is to discover scientific laws, is to recover the dynamics itself. And this is something I intentionally skipped during today's talk, because as you can see, I talked mostly about using gradients to compute, compute gradients with respect to parameters. I didn't talk too much about how gradients can be helpful for discovering new models or new partial differential equations, because this is something that I believe gradients might and probably won't be the only solution. It's unlikely to be a solution, actually. And I believe this actually requires multidisciplinary collaborations from other fields like symbolic AI, numerical optimization, and physics to fully resolve these exciting problems, to discover scientific laws behind the data. And I'm still thinking about this because I think as an advocate of gradient-based approaches, I still have a lot of thinking to do before I can answer how gradients can be helpful. But hopefully, from today's talk, I hope people from other backgrounds can share some thoughts on this and agree that we have provided something that might be useful, something gradient-based that might be useful for all of us to build towards a solution that can answer this question satisfactorily. OK, so that concludes my talk. I would like to end the talk with acknowledgments to the funding agencies and acknowledge the figures from and the reference papers I talked about. And the code and data and papers are all available online. They're publicly available. And that ends my talk. And I'm happy to take questions from now on.
Thank you so much for the great talk. I think we can also have questions from the audience or from Zoom.
Yeah. And thank you for having me there. Sure.
So the 40K dots, are they the box representing the fish itself? Or?
Yeah, roughly speaking, they are the number of voxels, the underlying regular grids that actually encapsulates the fish.
Okay.
Yeah.
And then for the basic design of the fish, did you collaborate with people who know the categories of fish to come up with the basis, like the 3 and the 12?
Yes, so they were mostly extracted from previous literatures, from computer graphics, from marine biologists, and we basically, this was the handcrafted part. We basically manually picked a few, I think up to 10 or 12 different base designs that we believed are reasonable enough, and then we constructed the interpolated design space. We kind of think that it is possible to scale this up to maybe, I would say, 20, 30, or 50 different base shapes. But if you want to do a more, I would say, a true exploration of different fish types, you will have to think about something that I would say slightly differently, because I don't think it is easier to scale this up to hundreds or thousands of designs.
So maybe I'll ask a question. I was curious how you use the gradients to disentangle the appearance from the dynamics.
Yes.
In your last example.
Yeah.
Because of course, particularly the foreground is very different from the background, right?
Yes,
The dynamics will also impact appearance.
Yes. So I intentionally skipped the technical part of this work. So the technical answer to that is that we used the differentiable renderer that our colleagues developed at MIT. And differentiable renderer plays a similar role in this visual appearance pipeline, just as differentiable simulator plays a role in inverse dynamics pipelines. So with the differentiable renderer, we were able to calculate the gradients with respect to the background color, like the lighting conditions, and we enforced, during the training process, we enforced this gradients to be as close to 0 as possible. And this is going to be something that you cannot achieve exactly because you are training a network to approximate things. But this is a strong enough bias for the network to learn to forget about these irrelevant variances. Yeah. And the interesting part that we figured is that without this trick, you will have to suffer from the network will have a very hard time understanding what you are asking it to teach, to memorize. And it will memorize something about the variations in the foreground, variations in the background, because you have no strong incentive to let it forget. Yeah?
I've got one. So I want to carry on that same example. It seemed with the quad rotor and the hand that a lot of the examples were based on sort of well-defined kinematic systems.
Yes.
What do you think is necessary to transition more towards soft systems that are, say, underactuated or underdefined? Not necessarily underdefined, but underactuated.
Yes, yes. This is a great question. And this is also a limitation that we discussed in the paper. There are a few assumptions that this work assumes. One of them is that you kind of expect the dynamic model itself is reasonable enough to characterize the real-world motion. For example, for the quad rotors, there are some dynamics we did not model, like the battery and like the propeller itself. We used a simple enough rigid body dynamics. And but I can assure you, if you use a mass, if you just use mass spring to replace the rigid body dynamics and rerun the pipeline, it's going to fail because then in that case the discrepancy between the dynamic model will be too much to absorb, and you cannot simply push the network to absorb this. So I don't have a quantitative answer to your question, like how much discrepancy is tolerable for the network to keep running as a euro. But I think the experience is that try to model as much as possible that whenever you can use physics laws to understand. And for those that it's hard to model, give network a try. For example, we did not model batteries because we thought battery was very hard to measure. And we were just praying that the network can succeed. And luckily enough, it succeeded. So we were happy, yeah.
Very cool, thank you.
Maybe I'll just ask one last one then, if that's okay. Why you mentioned that you skipped the limitations, so I'm very curious. Like, what do you think are problems that the gradient can solve, and why?
Yeah. So I think there are actually many things that gradients cannot solve. One thing that I think gradients is having a very hard time struggling with is to deal with discrete rules or discrete operations. And examples like for example, in CAD, you have different grammar rules to assemble the system, and this is something that inherently defined, not continuous or not differentiable. And so in this case, a discrete search will be much more powerful than running gradient descent. Even if how could you run gradient descent for this kind of problem? You would have to do some soft max and relax the problem, soften the problem, and it's going to getting less and less accurate. And another thing that I think gradients cannot solve alone is that you will suffer from local minima if you stick to local continuous-based continuous gradient-based optimization algorithms. So it has to have some kind of global sense of the problem, of the energy landscape, to basically rescue itself whenever it gets trapped into a local minima. And this is not necessarily something that can be solved using gradient descent or even using continuous optimization alone. You might want to have some kind of discrete taste in the problem. So it's hard to say what is challenging, and I'm a bad predictor here. But I think in the future, I would say it's probably we're looking for a hybrid solution that can take the benefits from each and every single direction here.
That's really inspiring. Thanks so much for the great talk.
Thank you again.
Right. Let's thank the speakers.